Hello. We'll talk about ICA, independent component analysis today. So basically, what we have is we start with originally k independent components, and instead of like having these k independent components, we actually have mixtures of these components. So let me just give a pictures that probably explain better. Let's say we have these three independent components here, and instead of having these three independent components, we got mixtures of these components like this. So this is one mixture, this is another mixture, and this is another mixture. And our goal is that to find back these original components. So, write it more precisely, we have S here is a matrix containing the independent components. Each row is one independent signal. So, in this case, S is k by n, so the length of each signal is n, and we have, in the previous example, k is equal to 3. So, for simplicity, we'll assume that we also have k mixtures of these independent components. So therefore, like these mixtures can be written as A, this is square matrix multiplied by S, and let's denote these mixtures as X. So each of these rows of X now is no longer independent. Each of the rows will be dependent on each other in general, unless A is, of course, a kind of diagonal matrix. And so the goal is basically we want to find back these independent components S, and we assume the whole thing is linear, so then we can also basically able to decompose this component best linearly. In other words, we want to find W or W transpose such that y equal to W transpose multiplied by X will be an approximate of S, or more precisely, like each of these rows here will be an independent component out of S. So as you will see later on that a key assumption for ICA to work is that S has to be non-Gaussian, or I should say like each of these independent components supposedly to be Gaussian. Drawing from a non-Gaussian, distribution. Did I say Gaussian? It should be non-Gaussian. So the key idea is pretty simple. Let's say, for the moment, we only want to extract one component, one independent component, and we write again y is equal to W transpose X. Now we only have one component, therefore W transpose is basically just a row vector, one row vector here. And as we have seen in the previous page, X is equal to AS, so we can write y is equal to W transpose AS, and W transpose A is equal to U. Let's denote as U is just a row vector again. So what we have here is basically, as you can see, y is just mixing this signal, independent signal S here, and by central limit theorem, if to start with S is non-Gaussian, let's say, then as we mix more and more S together, we'll get more and more Gaussian signal. So, or in other words, if we can ensure that we are going to pick the most non-Gaussian y. Let's say we're going to find some u such that y will be as non-Gaussian as possible. Then that u has to be only contain one non-zero component, or like y will be just getting it's getting from only one of these s here. So in other words, y will be just equal to one of the s. So that's basically the idea. So that's why we need S to be non-Gaussian. So if S is Gaussian, then basically this thing won't work, because to start with, we have something Gaussian already. There's no way we can make off something as non-Gaussian as possible. So, or like, of course, if you have all of them Gaussian, then there's nothing you can do. If some of them Gaussian, some of them non-Gaussian, then you can extract the non-Gaussian part out, something like that. So how do we measure the non-Gaussianality? So the traditional way is using kurtosis, but kurtosis is kind of sensitive to outliers. One very useful, or actually the ways we'll use here, is to use the lab entropy. That's basically, it's just equal to the entropy of a variable y Gaussian, which is basically same mean, not same mean, but same variance as the variable y, and minus the entropy of y. So because we know that by information theory, basically, Gaussian has the largest entropy for the fixed variance, therefore this thing here, this difference here, will be always positive, or positive, or basically will be greater than or equal to 0. And basically this will be equal to 0 only when y is also Gaussian. So, but the problem is that to compute this jy, this lab entropy, we need to compute the entropy of y. And to compute the entropy of y, we need the distribution of y itself. Basically, we need all the statistical information of y. So, and we basically don't want that. Instead, we just want to, actually it's sufficient to do, to compute an approximation of the lab entropy. So we can do an approximation by introducing a kind of measure function, we say g here. So basically, this will try to measure like how non-Gaussian a variable is. So hopefully, if it's far from non-Gaussian, then this variable will be different. Okay, let me say it again. So basically, what we are going to do is compute the difference between gy, the expectation of gy, and the expectation of g nu, where nu is basically a random variable, Gaussian random variable, with the same variance as y. So of course, if these two, if like y is also Gaussian, then this difference will be equal to 0. So in general, this will be non-zero. So we want, okay, there's some good choice for g will be like this one. So we can pick g as this 1 over a log hyperbolic cosine of ay. And in general, we can take this approximation as sum of several of these square differences, but in practice, usually we just use one square difference. For example, we can use this square difference we just mentioned here. And before I go to the algorithm, the FastICA algorithm, I just want to show that really minimizing the Gaussianity is the same as maximizing independence. So first, let's see the mutual information between random variables. Let's define this mutual information as the KL divergence between the joint distribution and the product of distribution, marginal distributions. So using this definition, okay, honestly, this definition is introducing mutual information this way is what's that word? It's not a unique definition. There's some other authors actually use other definition. But let's say if we define it this way, then as long as x1 up to xn are independent of each other, then of course the products of the marginal distribution will be equal to the joint distribution. So therefore the KL divergence will be equal to 0. And of course, scale divergence will always be bigger than or equal to 0. So that means that only when we have independence, then we will have this mutual information equal to 0. Otherwise, it will be bigger than 0. Alternatively, we can expand this mutual information, or like this scale divergence expression, as this one, and then we'll get we'll get this expression here, hx1 plus the sum up to hxn minus the joint entropy. Now, let's say we have y equal to w transpose x, and this is okay. Again, we are trying to find this w transpose such that this resulting y will be mutually independent. So we want to find this mutual information of this y here, and before that we need to find the joint entropy of y. Now, for that one, we need to know the distribution of y, the PDF of y, and the PDF of y can be written as the PDF of x over this determinant of w, the size of the determinant of w. The absolute value of this determinant w. And with a little bit of algebra, okay, you can see that that joint entropy of y will be just equal to the joint entropy of x plus log determinant w. So therefore, I can write the mutual information of y as hy1 up to hyn minus the joint entropy is equal to hx plus log determinant w. So it's minus hx minus log determinant w. So if we assume y is center and whiten, that is the expectation of y transpose is an identity matrix. Then this y I can write it as WE expectation XX transpose W transpose, and therefore determinant W is equal to this guy here, determinant expectation XX transpose to the square root, taking the square root, and the key point is that this is a constant. So now the mutual information can be written as, again, as you can see, basically I'm splitting the first term of the sum here as sum of the net entropy, or sum of the minus net entropy plus sum of the entropy of the Gaussian random variables that have the same variance as yi. And besides the first term here, all the rest of the terms are basically constant. So therefore, maximizing the left-hand side, the mutual information will be the same as minimizing this first term here, basically the sum of the net entropies. So now we can start talking about the FastICA algorithm. But before that, let's go through some pre-processing step. Let's say we say thing x. What we want to do is we want to make sure it's center and also whiten. So we basically center just means that we want to have zero mean, so we can simply subtract the mean to get zero mean, and then afterward it's whiten in the sense that the expectation XX transpose is an identity matrix. We can do that by simply replacing x by ed to the minus 1/2 E transpose x, where this ed E transpose is just an eigenvalue decomposition of expectation XX transpose, or the covariance matrix. So anyway, you can go through this very easily. This is basically very simple algebra again. So this is helpful, as you will see later. this simplifies some of this derivation, as long as we assume that x is center and also y10. Now get into the real algorithm here, the FastICA. It was introduced by Hyphanian. I really don't know how to pronounce his name. He's a Lofton European, and it's a work he did that in 1999, I believe. Again, the idea is very simple. So basically, we just want to maximize the long Gaussian ality. Basically, maximize the sum of the net entropies of all these components, subjected to the constraint that we want to make sure that the resulting y is also center in y10. So therefore, we want to have the expectation. This wk transpose x is basically just yk, and this is yj transpose. So we just want to make sure this is a delta function here. Actually, I think there's a typo here. The transpose should be here. But it doesn't matter. So again, the net entropy, we are using an approximation to compute the net entropy, will be equal to this square difference of the expectation of this measure function g here. And g function is, as we said, like one option here is to take the g function as this one here. And let's say if we just want to find one component at the moment, then instead of trying to maximize the sum of net entropies, we'll just maximize one net entropy obtained by just one component here, one w here. And since we only have one w also, then there's no wj, wk, we just have w. So we should have this is equal to 1. So because we already whitened the data, this w transpose x transpose, the expectation is equal to this guy here, and expectation xx transpose is still the identity matrix. Therefore, we simply have w transpose w is equal to 1. Now, just trying to solve this optimization problem here, we can just use Lagrange multiplier, very standard technique. So we absorb the constraint using a Lagrange multiplier here, and then we trying to take the derivative of this guy here with respect to w, and then we get this. Basically, we take derivative with w, then we have this beta w here, and take derivative w here. We first take the there's some notation here, is missing here. dg x is equal to gx. So this g is like a derivative of g here. And so this is basically a chain rule. We take the derivative of g first, and then take the derivative of w transpose x with respect with w transpose w. Then we get x back here. We call this thing supposing it should be equal to 0 at the optimum. So and we call this thing fw here. Now, first of all, what is beta here for the optimum w? Let's say the optimum w is w naught. Then we have this thing is equal to 0. Therefore, this expectation g w naught transpose x is equal to beta w naught here. And note that like this g here is actually a scalar. So but this is a vector. W naught is also a vector. We can multiply w naught transpose a vector on both on both sides, like from the left, let's say. So we have on the right hand side beta W log transpose W naught. This thing here, because we have the constraint that W transpose W is equal to 1, then this is gone, it's just equal to beta. So therefore beta is just equal to this guy here. And now, so how about finding the omega here, or finding the W here? So to find the W, we'll use Newton's method. Basically, W should satisfy Fw equal to 0, where Fw is equal to this guy, as we were given like previously. So to use okay, the Newton's method, just maybe remind of the viewer here, like if they are not familiar with Newton's method. Actually, the 1D Newton's method is very easy to understand. Basically, what it's trying to do is we are trying to, let's say this is a function Fw, let's say this is just a 1D function Fw here. We want to find the root at this point here, and let's say this is say the for the last iteration we get an approximate is equal to Wi here. Then for the next iteration, we will go down to this Wi plus 1 by basically taking this slope here, you move this way here to get to this point here. So the idea is that if you are in basically if a function is a straight line here, then if you have at this point here, let's say this is your Wi here, one step will go all the way to your root basically, very nicely. But also, of course, if your function is kind of at this point, if not actually the slope is not I mean this is not a straight line, then you go to here, then the next time you are at here, and then you go up, you go to here, and then go back and forth, and eventually go to the solution. So okay, what is this distance here? This distance is just Wi plus 1. Okay, Wi minus Wi plus 1. And this is actually equal to f over the slope, right? Or you can think of like slope is equal to Fw over this distance here. So you move things back, and then you will get this basically. For the next iteration, Wi plus 1, you should update it as Wi minus Fw over the slope. So for high dimensions, we don't have actually a slope, just a scalar. We have slope is basically like a matrix here, and it's actually the Jacobian matrix. So therefore, like instead of having Fw over the slope, we have Fw multiplied the inverse of the Jacobian. And the Jacobian, as I said, is a matrix here, defined this way. And let's just compute that. It's basically equal to taking the derivative over this f function here with respect to w. So taking derivative with respect to w, we have beta I here for this beta w. And for this guy here, we will have chain rule again. So first we take the derivative of g. We have g pi here, the derivative of g here. And then we try to take derivative of w, we get x transpose out here. So now it's this is an kind of tricky step here. Actually, the rest is all the direction up to now, everything is standard. There's nothing tricky here. Actually, this is the only tricky step the author did. Basically, he simplified his algorithm quite a bit, by assuming this is true. Basically, the expectation g pi times this xx transpose is equal to expectation g pi multiplied by xx transpose to expectation xx transpose. And basically, this is basically saying that he's assuming that this is decorrelated these two variables. When he didn't really explain much about it, he just have one statement there saying, okay, if x is center and whiten, then this is very much likely to be true, so therefore we can approximate that. So if we accept this, then things get simplified quite a lot, as again, like x is center and whiten, therefore expectation x transpose is equal to just identity matrix, and therefore we can pull this out. It's just equal to, okay, this thing here is just a scalar, g pi is a scalar, so therefore we have this expectation g pi minus beta, this one scalar multiplied by an identity matrix. And of course this is very easy to invert. Invert is just equal to I over this scalar here. So therefore we will have W now will be updated as W minus this FW is this thing here over this value here. Now this is for the case with one component, finding one component. You can do that. So if we need more component, the good thing for this algorithm here is that the Lagrange multiplier only find a local solution. So, and every time we are actually, as you can see, like for the iteration, we need to start with something. Therefore, every time we actually randomize W a little, find a randomized W to start with, and so therefore each time we will get a different solution. So ideally, we just do these things like k times, you will get the solution. Basically, get all k independent components. In practice, it may be possible that we'll get the same component as what previously have been found. So to make sure that we didn't find the same component as what we already found, we can use the typical Gram-Schmidt technique. So basically, let's say if I find a component yi, let's say I have prefix to yj. So what I just mentioned is that, like, we want to make sure these components are, if I is equal to j, it will be equal to 0. So this expectation should be equal to 0. Or like I and j should be orthogonal to each other. Oh, actually this is given earlier, right? This is the constraint we have all over. Yeah, that's the constraint we have at the beginning. And of course x is whiten, so therefore this constraint is really saying like yi transpose yj is equal to a delta function delta ij. Now let's say if we have w2, w1, w2 is one of the components we find, and w2 let's say we have w2 transpose w1 is equal to k, and let's say now we take w2 tutor as w2 minus k w1, then you can easily verify that now this new w2 tutor will satisfy this w2 tutor w1 is equal to 0. So that's what we want. So therefore we can simply update w2. Instead of having w2 as the candidate component, we change it to w2 minus w2 transpose w1 w1. When we pick this, then this will be orthogonal to w1. And of course we want to make sure that w1 is normalized, w2 is normalized, so therefore we have this normalized step also. So similarly, we can repeat the same thing if we have a new candidate w3. So instead of like just taking w3, we can subtract the component, subtract the components from subtract the previously found components using Gram-Schmidt, and then normalize it. Okay, then this is the whole basically the whole ICA algorithm. So to summarize, So we have a preprocessing step, basically do centering and whitening. And then afterward, for the fast ICA, we'll try to find one component at a time. And let's say we have already found like from 1 to the I-1 component. And let's say in the ith iteration, we're trying to define the ith component. We'll first just pick a randomized W, and then we'll update W using this equation here that we derived earlier. Here I also introduce a mu here. So remember, like previously, it's just W minus this expression here. So we'll pick a mu here. If mu is less than 1, this will increase the stability of the algorithm. So basically, you can pick like mu equal to 1 at the beginning, but if you have problem like curve converging, then we can pick a smaller mu. Then afterward, we just want to make sure that like W will be independent or like orthogonal to all the other components. So we use Gram-Smith, basically subtract all the other components, and then we normalize W. And that's all basically. And again, like, let me show you how this thing works actually, or like how good it works. So this is, as we mentioned at the beginning, this is like 3 independent components, and we have getting 3 mixtures here, and this is the input to the fast ICA algorithm. Now using the fast ICA algorithm, we'll get something like that. This is the solution. This is almost getting exactly as the original. This is actually really impressive here. But you can see like this is not exactly the same. Like this sinusoidal here is flipped because we're only getting the independent component up to a, of course, a scaling factor. So therefore it's or like the scaling factor does not affect the component. And we have basically in this case we have a -1 scaling factor for this sinusoidal. But in any case, like this thing, the fast ICA algorithm is actually very simple and at the same time it's very efficient and very impressive. And that's all for me. Thank you for watching this.